So you're sitting in class, listening to your professor lecture on about dy this, dy that, and you can solve dy this, find the critical numbers of dy that, and everything in between. But have you ever wondered where this all came from?
Studying the history of mathematics is not the same as studying mathematics itself, but when learning math, it often helps to know something about its history. Calculus, as one of the most significant branches of mathematics, has applications in most scientific fields, including statistics, physics, and chemistry.
So, if you have ever wondered about where the very important subject of calculus came from, then you're in the right place. We will take you through a journey of mathematics by introducing two key figures in the history of calculus, Isaac Newton and Gottfried Wilhelm Leibniz. Then we'll move into a discussion of their discoveries and where these discoveries stand today. We'll also discuss a bit about calculus before Newton and Leibniz.
First, let's introduce Gottfried Wilhelm Leibniz, born on July 1st, 1646 in Leipzig, Saxony, now Germany. Leibniz's father, Friedrich, was a professor of moral philosophy. From a young age, Leibniz was deeply interested in logic, even being disappointed with Aristotle's system of logic, which he had learned in school. Around Easter of 1661, he entered the University of Leipzig as a law student, where he first came into contact with the ideas of many who had revolutionized science and philosophy, including Galileo, Francis Bacon, Thomas Hobbes, and René Descartes, among others.
On the other side of Europe was Sir Isaac Newton, born on January 4, 1643, in Lincolnshire, England. Newton didn't have an easy childhood. His father died before he was born, and he was separated from his mother for about a decade when he was only 2 years old. As an adolescent, he was reunited with his mother and was appointed to manage her estate for some time. His duties on his mother's farm kept him away from school, so he had very little exposure to arithmetic by the time he enrolled at Trinity College in Cambridge.
Although the debate of who discovered calculus first, Leibniz or Newton, was quite a hot topic back in the 1600s, it's generally accepted today that each of them discovered calculus around the same time, completely independent of each other.
Newton's journey to the discovery of calculus began when his university studies started to diverge from the works of Aristotle. When Newton began studying the works of Descartes and other more modern philosophers that viewed the world around them as a giant machine with millions of quantifiable moving parts, it was Descartes' logiometry that ultimately began Newton's path to discovering calculus.
Within a year of learning the topics in geometry, Newton had mastered the classical geometry and modern analysis. He still wasn't satisfied though. He began his own line of analysis and eventually perfected and formalized what we now know as the binomial theorem.
Similarly to Newton, Leibniz wasn't satisfied with Aristotle's logic. But unlike Newton, Leibniz didn't study mathematics rigorously until he was already a seasoned intellectual. In fact, he already had multiple degrees, including one in law. It was not long after finishing his studies in Leipzig that Leibniz met the Dutch physicist Christian Huygens.
Huygens suggested that Leibniz read St. Vincent's work on summing series. This work directly influenced Leibniz's development of calculus, especially in understanding integrations, which we will show was originally understood as summing series. Huygens later suggested other works of important mathematicians, including Pascal and Descartes. Pascal was very influential in the development of probability, while Descartes formalized many proofs and developed the idea of the Cartesian or XY plane.
Now we're going to shift over to talking about calculus itself. We'll discuss calculus in the order that it was discovered by Newton and Leibniz. Unlike the way you were taught in your calculus classes, calculus developed first from integrals, then as derivatives, and finally as limits.
The impetus for Newton's study of integrals was his work on the laws of motion. In Philosophiae Naturalis Principia Mathematica, published 1687, Newton proved many of the integral theories of calculus. A principal theorem involved finding the area under a curve. In Principia, the curve represented the motion of a moving object as it was pushed towards a central point. Newton utilized a combination of his knowledge of geometry based off of Descartes' methods and techniques and his study of infinite series. Next, Newton chose the circle defined as x minus 1/2 squared plus y squared minus 1/4 equals 0. Newton solved for y, getting y equals x square root times 1 minus x square root. Newton used his general binomial theorem and expanded his curve y equals square root of x times square root of 1 minus x as y equals x to the 1/2 times 1 minus x over 2 minus x squared over 8 minus x cubed over 16 minus 5x to the 4th over 128 minus 7 times x to the 5th over 256, and further expanded and got y equals x to the 1/2 minus x to the 3/2 minus x to the 5/2 over 8 minus x to the 7/2 over 16 minus 5 times x to the 9/2 over 128 minus 7 times x to the 11/2 over 256. In a previous work on analysis by infinite series, Newton proved what is now known as the fundamental theorem of calculus. Newton considered the area under the curve ACF. He set AB equals x, BD equals y, and the area ABC equals z. Next, he let BG equals O be an infinitesimal segment and took BD equals V, so that VO equals the area of rectangle BGED equals the area BGFC. Thus, AG equals AB plus BG equals X plus O, and thus it follows that the area AFG equals area of region ACB plus area of region BCFG equals Z equals area of rectangle BGED equals Z plus VO. If the increment of BGED equals VO is divided by the increment of O, then we get V. Since O is infinitesimal, we get V equals Y. Thus, dz over dx equals y, which shows that the antiderivative of a function within bounds gives the area of a curve within those bounds.
Newton referred to derivatives as fluxions. He wrote a piece on fluxions during the latter part of 1666. It was not published immediately, but was seen by many influential mathematicians. Newton's method of fluxions wasn't published till 1736. Newton also referred to fluxions as fluents. These were the basis of Newton's early calculus. Fluxion is the instantaneous rate of change. Leibniz's terminology for calculus is widely used rather than Newton's.
Here are some contributions that Isaac Newton made to calculus. He calculated the derivative of any algebraic curve by using infinitesimals and implicit differentiation. In addition, he worked out the chain rule and showed how to take derivatives of products and quotients. He used an intuitive argument to show what we would phrase by saying that if A is the area under the curve y equal f of x, then dA dx equal y, which is the fundamental theorem of calculus.
Beyond that, he also computed a table of antiderivatives, in part using integration by substitution, where some of the antiderivative were given explicitly and others were handled with the binomial series. And that was basically the birth of calculus.
As a sort of rival of Isaac Newton, Leibniz worked on derivatives and integrals utilizing infinitesimals, which are extremely small quantities approaching zero. Leibniz used his study of infinitesimals for functions where y is a function of x, and so as x changes, y may change too. Leibniz defined derivatives as infinitesimal changes in y and x as dy and dx. It's worth mentioning that Leibniz was very conscious of the importance of good notation and put a lot of thought into the symbols he used.
Newton, on the other hand, wrote for himself to read and understand. Consequently, he tended to use whatever notation he thought of on that day. This turned out to be important in later developments. Leibniz's notation was better suited for generalizing calculus to multiple variables, and in addition it highlighted the operator aspect of the derivative and integral. As a result, much of the notation that is used in calculus today is due to Leibniz.
Specifically, Leibniz worked out the derivative of power functions, as well as the product rule and quotient rule, writing everything in terms of differentials rather than derivatives. Also, he observed that if v is the function, dv is positive when v is increasing, and analogously for decreasing, and hence that local extrema occur only when dv equals 0. More importantly, he concluded a significant thought that we can view integrals as a type of sum and differentials as a type of difference, and hence integrals and differentials had an inverse relation.
Leibniz discovered the method of integration in essentially the same way as Newton, which is one of the reasons Newton believed so adamantly that Leibniz plagiarized his work. The most insignificant contribution that Leibniz made to the method of integration that hadn't already been done by Newton is the notation used to express an integral.
As we mentioned earlier, Newton's writings was mostly for himself, so the notation wasn't very clean or easy to understand. Leibniz, on the other hand, began using what we know as the elongated s used to represent. Like his notation for derivatives, this is still the notation mathematicians use today.
Ultimately, Newton and Leibniz were the first to combine the knowledge of earlier mathematicians, logicians, and philosophers into what we now know as calculus. While Newton and Leibniz laid the groundwork, calculus was further developed by pioneers such as Euler and L'Hopital, both names any calculus student is familiar with. Calculus was developed and proven even more rigorously through the 1800s into the 1900s.